Hello everyone and welcome back. Well, in the previous lecture we have discussed in details about clique and independent sets in a graph. We have learned how to find out the maximal and maximum cliques and independent sets also. And in accordance with that, we have learned how to determine the clique number and independence number of any given graph. Well, in today's lecture, we will be dealing with yet another very important topic of graph theory, a very important type of graph called the bipartite graph. In relation to that, we will also be learning in details about the complete bipartite graph, a particular type of bipartite graph. So, without any further delay, let's start today's lecture with this vital concept called bipartite graph. Now, before I get into the very topic of bipartite graph, it's very important that we have a very clear idea about partition of a set. So, let us first discuss in details what do we mean by partition of any given set. So, suppose we have a set S containing some elements. Let's suppose this is our set S. What do we mean by partition of this set? By partition we mean we divide this set into a collection of subsets such that every subset of this collection would be non-empty. If we pick any two subsets of that collection, we will find they are disjoint sets, and all these subsets taken together, that is their union, will give us the whole set S. Let's see how. For example, if I take a subset A1 of this set which contains the elements B and G only. Let me take another subset A2 which contains A, M, N and Z, and I take another subset of S which contains C. So here we have three subsets of S. Each set is non-empty. This is not equal to 5 because every subset is containing at least one element. So none is empty set. And if we take any two subsets among these three, suppose A1, A2 or A2, A3 or A1, A3, we will find those subsets are mutually disjoint sets. They do not have any common element between them. Another important thing is, if we take a union of these three subsets all together, we will see we are getting the whole set S. So let me just list down the important points that one should keep in mind while creating the partition of any set. So we say that a collection of subsets A1, A2 up to AN is a partition of a set S if the following conditions are satisfied. First condition, each AI is non-empty set where I runs from 1 to n. So each AI, be it A1, A2, A3 up to AN, everyone should be non-empty. We should not consider an empty set in a partition. Second point is AI intersection AJ should be equal to 5, where definitely I is not equal to J and both of them lie within this range 1 to n. And without loss of any generality, we have assumed I is less than J. So what does this point mean? Basically, it means that any two subsets from this collection of subsets will be disjoint. That means no two subsets of this collection will have a common element among them. And definitely we are talking here about two different subsets taken from this collection. That is why I should not be equal to J. And the third point is, if we take the union of all these subsets, that is I am taking the union of all the AIs, I running from 1 to n, then that union must give me the whole set S. So these 3 points are to be kept in mind while creating the partition of any set. And one more important thing to mention here is that every subset of that partition, that is each AI, is called partite set. So to summarize, basically a set will have a partition into a collection of subsets which are called partite sets only when each of these subsets will be non-empty. No two should have a common element, that is every pair of subsets should be mutually disjoint, and the union of all these subsets taken together should give the whole set S. Now let's come to the concept of bipartite graph. Now in order to call a graph bipartite, one should keep in mind two important points. If satisfied, then we can call the graph bipartite. Now the first point is that the vertex set of the graph should be partitioned into exactly two partite sets. And in what way? That is the second point. The partition of the vertex set should be such that every edge in the graph will have one of its endpoint in one partite set and the other endpoint in the other partite set. Now that's all about the definition of bipartite graph. Let's see it and visualize with the help of an example. Let's take a graph G. Suppose we have this graph G with the vertex set ABCD. So let's write the vertex set of this graph, that is the set containing the vertices A, B, C, D. Now if this graph G has to be bipartite, then we would be able to have a partition of this vertex set VG into exactly two partite sets. Now when we talk about partition of any given set, for example here VG, we can have many ways of having a partition of VG into two partite sets. But we need a particular partition of this vertex set. So what is that condition which should be satisfied? The condition is VG should be partitioned into two sets such that every edge in your graph G should have one endpoint in one partite set and the other endpoint in the other partite set. Let me have a partition of VG for you. Suppose I take a subset A1 containing A and C, and I take a subset A2 containing B and D. I can call this a partition because both the sets are non-empty, their intersection is phi, they are disjoint subsets, and their union gives the whole set VG. So the collection of the two sets A1, A2 is actually a partition of the vertex set VG. So first point is satisfied, but the second point is equally important. I have to check whether this partition is such that every edge in the graph is having one endpoint in one partite set and the other endpoint in the other partite set. That must happen. So let's see, for example, this is an edge in the graph AB. So we have to make sure this edge AB is having both the endpoints, that is A and B, in two different partite sets. So here we can see that the vertex A is belonging to the partite set A1 and the vertex B is belonging to the partite set A2. That means the edge AB is having both its endpoints in two different partite sets. That is what we need. Then come to the next edge BC. So here the end vertices are B and C. See, B is in one partite set, C is in the other partite set. Then we come to edge CD. C is in one partite set, D is in the other partite set. Next we come to the edge AD. So A is in one partite set and D is in the other partite set. So for every edge of the graph, we see one of its endpoint is in one partite set and the other point is in the other partite set. So that is what is required for the graph to be bipartite. So 2 points are to be remembered here. First, the vertex set should be partitioned into exactly two partite sets, and second point is the partition should be such that every edge has one of its endpoint in one partite set and the other in the other partite set. Now the crucial part is to determine the correct partition of the vertex set. Now there is a technique of doing that as well. So let's see how we can decide the correct partition of the vertex set at once. What we will do is, given any graph G, now let's draw the same graph G in the suitable orientation of a bipartite graph. Let's see how a bipartite graph looks like. The same graph will have a different orientation, which is basically the standard orientation of any bipartite graph. See, I already have my partite sets here. What we have to do is, we have to keep the vertices of one partite set in one row. So, since capital A1 is one partite set and the vertices included in capital A1 are A and C. So, A and C, these vertices should be kept in a single row, that is in one horizontal level. And the vertices of the other partite set, capital A2, that is B and D, should be kept in the other level, BD. So we have to create two rows basically, because we have a partition into exactly two partite sets. So we will have two sets of vertices and we will place them in two horizontal lines. Now we are going to draw all those edges present in our graph. AB is an edge in the graph, so I draw the edge AB. AD is an edge, I draw the edge AD. BC is an edge, so I make B and C adjacent, and CD is an edge, so I draw the edge CD as well. See, this is the same graph G drawn in a different orientation. I have just redrawn the figure by swapping the positions of few vertices, and this is what the structure has become. So let me just explain to you the standard orientation of a bipartite graph. It actually has the structure such that the vertices of one partite set should be placed in one particular row and the vertices of the other partite set should be placed in a different row. Which partite set should be placed below or above doesn't matter. You can place any one above the other. Just you have to make sure you are creating only two rows for the vertices, and all the vertices of one partite set should be present in one particular row. Then every edge of the graph will have one of its endpoint in one partite set and the other endpoint in the other partite set. That is, every edge will have one of its endpoint in the upper row and the other endpoint in the lower row. This has to happen because that is how the partition of the vertex set has been made. So let us now discuss in details how to get to this particular partition, the correct partition that will give us this particular standard orientation of bipartite graph. Now let's see another example. Now one thing that we should keep in mind is a bipartite graph is always a simple graph. So here we are dealing only with simple graphs, so there is no question of having loops or multiple edges in the graph. So let's draw another graph and check whether it is bipartite. If it is bipartite, then what are the partite sets? What is that partition of the vertex set? So here I am taking the vertices A, B, C, D, E, F. So that makes my vertex set VG containing these vertices only. Now what would be the suitable partition of this vertex set VG so that my condition of bipartite graph is satisfied? Now in the previous example, it was very easy to create the required partition. So we created the partition in the very beginning, but that is not in general what we do. We first try to redraw this given graph in the bipartite structure. Now if it falls into that bipartite structure, we will be getting the partite sets very easily and automatically. And in case if the graph does not fall into the bipartite structure, then clearly the graph is not bipartite graph, and if it is not bipartite graph, we won't be getting that partition we were searching for. So let's redraw the graph in the bipartite structure and see if we can do that. So let us try to redraw this graph and see if it fits into the bipartite structure. So what we will try to do is, we will try to create exactly two rows of vertices. Now which vertices are to be placed on which row, that is what we need to decide. So let's start redrawing the graph and start with any vertex you want. I choose A. So let's start with A. Now since AB is an edge, so that edge must have one endpoint in one partite set and the other endpoint in the other partite set. So definitely the other endpoint B of the edge AB should lie on the other row of vertices. So here I should have my B so that AB is the edge of the graph. So this is how I draw the same edge AB in a different orientation. Now from A we see there is another edge AF. Since A is lying here and AF is an edge, so the other endpoint F must lie on the other row of vertices, not on the same row as A. So F should lie on the same row as B. So here we have the edge AF. Then from B we have an edge C. So if B is in this level, C should be on the other level of vertices, and this is the edge BC. So this edge is done. You can mark the edges once you complete drawing that. Then from C we have CD. So if C is in this level, then D must be in the lower level. This is D. This edge is done. Then DE is an edge. So from D, I draw an edge where E lies on the other set of vertices. So ED is an edge, that is done. Lastly, we have the edge EF. See, already your E is in one level of vertices and F is on the other row. So we have an edge EF. That creates the bipartite structure for the graph G. So basically the bipartite graph has two sets of vertices, which is actually the partition of the vertex set, because both the sets of vertices both are non-empty, they are disjoint, no vertex appears twice in both the partite sets, right? So they are disjoint and their union gives the whole vertex set. Secondly, every edge is having one of its endpoints in one partite set, other endpoint in the other partite set. That is the reason every edge is in a standing or slanting position. No edge will be horizontal, that is, there is no edge between any two vertices of the same partite set. Each partite set is free from any edge among themselves. All the edges are between vertices of either partite sets. So once we see that our graph can be drawn in this particular structure maintaining the criteria of bipartite graph, we can claim that our graph G is a bipartite graph. And one more important thing, bipartite graph is also called bigraph. Now once you get the graph in the bipartite structure, you can easily determine the partite sets. What are the partite sets? These vertices and these vertices separately create the two partite sets. In general, we represent them by U and W. So U is one partite set containing the vertices A, C and E, and W is the other partite set containing the vertices B, F, D. Well, now let me just summarize the very idea of bipartite graph. A bipartite graph or a bigraph is a simple graph in which the vertex set is partitioned into two partite sets. The moment I say partitioned, it includes the concepts that the subsets are non-empty, they are disjoint, their union gives the whole set VG. So if I need not mention these points, I should cover it up in one single word, that the vertex set is partitioned. And if you don't want to use the word partitioned, then you have to mention that the vertex set is divided into two non-empty subsets which are disjoint and their union gives the whole set VG. This is the definition of partition that you should include. And if you want to avoid it, you just cover it up by one word, that the vertex set is partitioned. Once the vertex set is partitioned, you should mention that the partition is such that every edge has one of its endpoint in one partite set and the other endpoint in the other partite set. Now one very important point to note here is that since we have already discussed about clique and independent sets, so it would be easy to understand. In a bipartite graph, the partite sets that are formed, each partite set is itself an independent set. Recall, independent set is a set of mutually non-adjacent vertices. See a partite set, this is a partite set ACE. You pick any two vertices of this set, you will find they are non-adjacent in the graph. AC non-adjacent, CE non-adjacent, AE non-adjacent. Again move to the other partite set. This is also an independent set of vertices because every pair of vertices here are non-adjacent in the graph. So the two partite sets basically are independent sets. That is the reason there is no adjacency between any two vertices of one partite set. The only adjacencies are between the vertices of the different partite sets. So this is the very definition of bipartite graph or bigraph. It is a simple graph in which the vertex set VG can be partitioned into two independent sets called partite sets, such that every edge of the graph joins a vertex of one partite set and a vertex of the other partite set. Let's see some more examples. Suppose this is my graph G. The question is, check if this graph G is bipartite graph, and if it is, then construct the two partite sets. So we will first try to redraw this graph in the bipartite structure. So let us start redrawing the graph G, and I start with the vertex U suppose. Now since UV is an edge in the graph, and if the vertex U is in one row, then the other endpoint V must be on the other row. Then we have Vx, V is here, so X should be on the other level. XW, X is here, so W should be on the other level. WY is an edge, W is here, Y should be on the other level. And lastly, we have the edge UW. Let us see if it satisfies the criteria. So U is here, W is here. It is fine with me to draw an edge between them, maintaining the condition that every edge has one of its endpoints in either partite set. So the graph falls into the structure of bipartite nature, and hence we get the graph as a bipartite graph, and the partite sets would be U is the set containing the vertices small u, x and y, and the other partite set is W containing the vertices v and w. So here is the example. So whenever you are asked to check if a graph is bipartite, do not jump into creating the partite sets. Start redrawing the graph. If it is bipartite, definitely it will fall into that standard orientation of a bipartite graph, and you will automatically get the partite sets. So start redrawing, just maintain the fact that you will be creating exactly two rows for the vertices, and every edge should have one endpoint in each row. Let's see another example. Suppose this is our graph G with the vertices labeled as U, V, W, X, Y, Z. So to check if it is bipartite, we will start redrawing the graph. Start with a vertex, suppose Z. Now from Z there is an edge ZU, so U should be on the other level. From U we have UV, so V should be on the other level than U. Then from V we have VW, so V is here, W should be here. From V again we have Vy, so V is here, Y should be here. For every edge that property has to be maintained. Now from W we have Wx, if W is here, X has to be on the other level. Xy is an edge, if X is here, see Y is on the other level, so it does not violate that structure. And finally Yz is an edge and we have Y and Z in different rows. That means we can draw the graph in the bipartite structure, which means it is a bipartite graph and the partite sets are ZVX, another partite set UWY. See, we don't even have to think to create the partite sets. We will get the partite sets automatically from the structure itself. So this is the example. Now let's check for another graph. Let G be this graph. So let's redraw the graph G. So I'll start with any vertex. Suppose I start with V. Then from V I have an edge VU. So if V is here, U should be on the other row. From U we have an edge UW, so U is here, so W should be on the other row than U. So you have W here. From W we have WX, so W is here, so X should be here. From X we have XY, X is here, so Y should be here. From Y we have W. Now for the edge YW we find both the vertices belong to the same level or same row. Now this cannot happen if the graph has to be bipartite. But here, because the edge WY is present in the graph, I am bound to draw this edge, and this particularly violates the definition of bipartite graph. So immediately we conclude the graph is not bipartite. Done. Okay. So to check bipartite, we have to redraw the graph. Start redrawing the graph. It's very easy. Just keep the edges up, down, up, down, up, down, and if at any situation you find you are bound to draw an edge between any two vertices on the same row, immediately conclude the graph is not bipartite. Else, if you can draw the graph in the bipartite structure, then definitely you will term it as a bipartite graph and you will give the partite sets also. Let's see for another graph. Suppose this is graph G. So to check whether it is bipartite or not, let's redraw. So I start with suppose Y. From Y I have an edge YU, so U should be here. From U I have UX, so if U is here then X should be here. From X I have XW, so W should be here. From W I have WZ, so Z should be here. From W again I have WV, so W is here, V should be on the other level. From V I have VU, so this is U, this is V, they are lying on different rows. I can draw an edge without violating the bipartite structure. So this graph is bipartite. Just keep two things in mind. First of all, every edge of the graph should be drawn when you are redrawing the graph. No edge should be missed. Secondly, do not repeat any vertex. If a vertex is already drawn on some row, you have to deal with that only. Don't create that vertex again. So just keep that in mind. So here we get two partite sets U, Y, X, Z, V, and the other is W, that is U, W. So this is that particular example. As we can see, we have two partite sets here. Next we move to yet another important type of bipartite graph, which we call complete bipartite graph. Now first important part of complete bipartite graph is that it is not a complete graph. Complete bipartite graph, although has the word complete, it is not a complete graph, so don't get confused. So let's see a graph G. Well, first let me deal with this. Okay. Can I call this graph bipartite? See, here I have 4 vertices in total. The vertex set of the graph is set containing U, V, W, X. I have divided the entire vertex set VG into 2 subsets, UV, another one is WX. Both are non-empty, disjoint, and union creates my capital VG. So this is a partition of the vertex set into 2 partite sets, no doubt. The edges which are present in the graph are UW and UX. Now see, the edge UW has one vertex in one partite set and the other endpoint in the other partite set, and the same is for the edge UX also. So it does not violate our definition of bipartite graph. So this is a bipartite graph. So you can have isolated vertices also. Now let's see if the same graph G can be called complete bipartite or not. Now when we discussed complete graph, we understand from the term complete that the graph is complete with respect to the edges. It has all those possible edges that it could have, keeping the graph simple. There is no more possibility of inserting any more edge in the graph. Now when we talk about complete bipartite graphs, it is not a complete graph, but it is complete bipartite, means keeping the bipartite nature intact, it is complete. Keeping the bipartite nature intact means you have two partite sets, and the fact that the two partite sets are themselves independent sets, that is, they are mutually non-adjacent vertices. You cannot have an adjacency among any two vertices of the same partite set. That is what is to be maintained when it is a bipartite graph. How can I make it a complete bipartite graph? By drawing all possible edges that I can, keeping it bipartite. That is, by making every vertex of one partite set adjacent to every vertex of the other partite set. Now see here, U is already adjacent to W and X, but V is not adjacent to any of W and X. That is the reason this graph is not a complete bipartite graph. Okay. Now let's see how can I make this graph a complete bipartite graph. Now if I make the vertex V adjacent to W and also adjacent to X. Now see, I have made every vertex of one partite set adjacent to all the vertices of the other partite set. Is there any more possibility of inserting edge in this graph, keeping it bipartite? Answer is no. First of all, we are dealing with simple graphs, so there is no question of loops and multiple edges, so they are not the entries anyhow. Secondly, we are dealing with bipartite graphs, that means the partite sets are independent sets. We cannot draw edges between any two vertices of the same partite set. So no how we can have an edge UV or an edge WX. So they are not an option. Apart from this, is there any more possibility of drawing an edge? No. All the adjacencies that could have been possible for this bipartite graph have been drawn. So in that sense, it is called complete bipartite graph. Let's see and draw a complete bipartite graph with these partite sets. Suppose U, V, W is one partite set, X, Y is the other partite set. So how can I make this a complete bipartite graph? It is bipartite, so I have two rows of vertices. Those partite sets are independent sets, so there will be no adjacency among any two vertices of the same partite set. But all the possible adjacencies between the vertices of the different partite sets, I will draw all those edges. So I will make the vertex U adjacent to all the vertices of the other partite set, that is X and Y. Then I move to V and make it adjacent to all the vertices of the other partite set. Next I move to W and make it adjacent to all the vertices of the other partite set. You will find automatically for the other partite set also, X has been already made adjacent to all the vertices U, V, W of the other partite set. Similarly, Y is also adjacent to all the vertices of the other partite set. So now there is no more possibility of inserting any more edge in this graph, keeping it a bipartite graph. This is a complete bipartite graph. So these graphs, suppose G1 and G2, these are complete bipartite graphs. Now complete bipartite graph has another name. It is also called biclick. I will definitely explain the reason to call it a biclick. Now before that, let me discuss the notation of a complete bipartite graph. Now just like a complete graph has the notation Kn, where n denotes the order of the graph, the complete bipartite graph also uses the same letter K, and in the subscript it has two elements, M, N, where M and N denote the orders of the two partite sets, because in a bipartite graph we have two partite sets. In each partite set we have some number of vertices. That order for each partite set, the cardinality of the partite sets are denoted by M and N. So we write that in the subscript. So how can we draw a KMN given any value of M and N? For example, suppose we need to draw K23. What will be this graph K23? So from the notation we have to understand K indicates complete. two elements in the subscript indicate it is complete bipartite graph. If it is a single element in the subscript, it is complete graph. So K23 is complete bipartite graph in which there are two vertices in one partite set and three vertices in the other partite set. So we draw that. We keep two vertices in one partite set and three vertices in the other partite set. Now it doesn't matter whether you put two vertices above or two vertices below. So name them U, V, W, X, Y suppose. So this is the vertex set of this graph. Now what about the edges? Because it is complete bipartite, so we choose a partite set, we pick a vertex, make it adjacent to all the vertices of the other partite set. Move your focus to the next vertex of that partite set, make it adjacent to all the vertices of the other partite set. So we are done with this partite set. We will see automatically the other partite set also has every vertex being adjacent to all the vertices of the first partite set. So this is what is a complete bipartite graph. See, we cannot draw any more edge in this graph, keeping it bipartite. So this is K23. So given any values of M and N, we can draw the complete bipartite graph. So now let's discuss why is a complete bipartite graph also called biclick. Now what is click? In the last lecture we have discussed click is a set of pairwise adjacent vertices. Now in a complete bipartite graph, you will find only clicks of size 2. See, you will find UW is a click, UX is a click, UY is a click, VW is a click, Vx is a click and Vy is a click. You will not have any other click of any larger size. Basically, the participating vertices of every edge will create a click and you will have only clicks of size 2. Now this bi stands for 2. So that is the reason we call complete bipartite graph biclick, because here every click is of size 2 only. So let's see the definition. A simple bipartite graph is said to be complete bipartite or biclick if each vertex in one partite set is adjacent to all the vertices of the other partite set and conversely. So basically make every vertex of one partite set adjacent to all the vertices of the other partite set. This is how we create the complete bipartite graph. It is represented by Kmn, where M and N denote the number of vertices present in the partite sets. So let's see the very first few complete bipartite graphs. So here we have in the very first example K01 or K10. Observe it carefully. Here we have 0 vertex in one partite set and 1 vertex in the other partite set. See, the order doesn't matter. You can write K23 or K32. It will be the same thing. The graph will be same. So here we have 1 vertex in one partite set and the other partite set has 0 vertex. So it does not have any vertex. So there is only 1 vertex present and there is no question of having any edge then. That is the reason the very first complete bipartite graph looks like this. And this is same as the complete graph K1. So this is an example of a complete bipartite graph which is also a complete graph. This is K1. Next we move to the bipartite graph which is complete bipartite K11. Now here we have 1 vertex in each partite set. So we have P, a vertex in one partite set, Q, a single vertex in the other partite set. Possibility of edges only 1. There is 1 edge possible between P and Q, so we draw that. This is complete bipartite K11. Now if you recall, this is the same graph as K2. So this is also an example of complete bipartite graph which is a complete graph K2. Next we move to K12 or K21. Now here when M and N are different, the order does not matter. Both are the same graph. 1 vertex in one partite set and 2 vertices in the other partite set. Possible adjacencies are PQ and PR. See, this is not a complete graph. This is not a complete graph because Q and R are not adjacent because it is bipartite. So the only complete bipartite graphs which are also complete graphs are K01 and K11. Apart from these, any other complete bipartite graph is not a complete graph. Next few we have drawn here. K22, so you have 2 vertices in each partite set and we draw all possible adjacencies between the vertices of either partite set. Then K23 or K32, so 2 vertices in one partite set and 3 vertices in the other. Order doesn't matter, you could have drawn 3 vertices above, 2 vertices below, same thing. And then you draw all possible adjacencies. Make every vertex of one partite set adjacent to all the vertices of the other. Do this for every vertex of one partite set and you were done. Here we have K33, that is 3 vertices in each partite set. Now let's discuss some very important properties of the complete bipartite graph KMN. Now KMN means there are m vertices in one partite set and there are n vertices in the other partite set. Now it is complete bipartite means every vertex here is adjacent to all the vertices below. Same holds for the other vertices also. Dot 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 means there are many more vertices I have not drawn. Okay, so this is the idea. So you will see every vertex of this partite set is adjacent to all the vertices of the other partite set which contains n elements. So the degree of every vertex in this set is n. This vertex is adjacent to n vertices below. This vertex is also adjacent to n vertices below. So its degree is also n. So all the vertices will have degrees n like this. Similarly, if you see the same thing with respect to the other partite set, this vertex is adjacent to all the vertices above where there are m vertices. So the degree of this vertex is m. Similarly, every vertex in this partite set have degree m. So basically in KMN, if U is the partite set containing m vertices, then every vertex here has degree n. And if W is the other partite set containing n vertices, then every vertex in W will have a degree equal to m. Okay. Now what is the order of KMN? The order of KMN means the number of vertices in total, that is the sum total of the number of vertices of the two partite sets, that is m plus n. There are m vertices in one partite set, n vertices in the other. So sum total is m plus n, that is the order of the complete bipartite graph KMN. Now what is the size of KMN? How many edges are there in KMN? Now to calculate the size of a complete bipartite graph, let us see for any bipartite graph G, how can we calculate the size? Suppose this is a bipartite graph G, it is not a complete bipartite graph obviously. So U, V, W, X, Y, these are the vertices. Now focus on one partite set U that contains the vertices U, V. What is the degree of this U? 2. The degree of V is 2. See the number of edges 1, 2, 3, 4. Sum of the degrees of U and V 2 plus 2, 4. You can check for the other partite set W, X, Y. This partite set degree of W is 2, degree of X is 1, degree of Y is 1. So sum of the degrees 2 plus 1, 4, number of edges 4. That means in any bipartite graph basically, if we know the degrees of the vertices of any one partite set, we sum the degrees of all the vertices in that particular partite set, we get the size of the graph. The same thing we can do for the other partite set also. So basically in a bipartite graph, be it complete bipartite or not, if we add up the degrees of the vertices lying in one partite set only, we can get the size of the bipartite graph. That is the reason summing up the degrees of all the vertices in this partite set gives me the size of the graph. Again, summing up the degrees of all the vertices in this partite set also gives me the size of the graph. So that is the reason, since complete bipartite graph is also a bipartite graph, so here also focusing on any partite set, if I know the degrees of the vertices, like here I know every vertex here is adjacent to all these n vertices. So here everyone has degree n. How many vertices are there in this partite set? M vertices. So each vertex having degree n, sum total of the degrees would be n plus n plus n. How many times? M times. That will give us the total value as m into n. So the size of the complete bipartite graph KMN is m multiplied by n. You can find out the size with respect to the other partite set also. See, here we have n vertices, each vertex has degree m because every vertex is adjacent to m vertices of the other partite set. So every vertex has degree m and there are n vertices in total. So sum total of the degrees would be m plus m plus m up to n times. So the total is again m into n. So Mn is the size of any complete bipartite graph Kmn. Now in particular, if we have Knn, that is same number of vertices are present in both the partite sets. For example, K33. So here you have 3 vertices in one partite set, 3 vertices in the other partite set. What will be the complete bipartite graph? It will look like this. Okay, this is K33. See, here there are 3 vertices, here also there are 3 vertices. So every vertex here is adjacent to all the 3 vertices below. Degree is 3. Same for all these 3 vertices, right? In the other partite set also, here every vertex is adjacent to all the 3 vertices above, so making its degree 3. So if basically we are talking about a complete bipartite graph where we have the same number of vertices in both the partite sets, that is suppose they are of the form Knn, then that is n regular graph. Every vertex will have the degree n. Like K33 is 3 regular graph, a graph where every vertex has degree 3. So Knn is n regular graph where every vertex has degree n. So these are the key points that we have just discussed. Now we will discuss some key points related to complete graphs and bipartite graphs with cliques and independent sets. Now let's talk about complete graph first. In complete graph Kn, you will see, since every vertex is adjacent to every other vertex, that is the reason the largest or the maximum clique that you will find is the clique which contains all the vertices of the graph. For example, if I talk about K3, I have this graph K3 U V W. See, K3 means complete graph where every vertex is adjacent to every other vertex. That means all the vertices can be included in a clique, and that will be the maximum clique because there are no more vertices in the graph. So all the vertices of a complete graph participate in a clique, and that creates the maximum clique. That is the reason the clique number of K3 is 3, 1, 2, 3. So the clique number of Kn is n. Any complete graph of order n, all the vertices will participate in a clique which will be the maximum clique only, and that will be of size n. That is the reason the clique number of any complete graph Kn is n. Now what about the independence number? See, for K3 itself, it is a complete graph, so every pair of vertices are adjacent. So no 2 vertices are non-adjacent here. So the only possible independent sets are the singletons U, V, W. That means the maximum independent set is also the singleton set only, which gives alpha of K3 as 1, and not only for K3, alpha of any complete graph Kn is 1, because we don't have even a single pair of non-adjacent vertices in a complete graph. Every pair of vertices are adjacent, so we can only have the singleton independent sets. Next we come to bipartite graphs. Now when we talk about bipartite graphs, be it complete bipartite or not, for example, this is the bipartite graph which has at least one edge. I am not talking about edgeless bipartite graphs. Now if it is so, then the maximum clique that you can find in a bipartite graph is of size 2. So for example, here we have UV. You will never find a clique of size larger than 2 in a bipartite graph. That is the reason omega of any bipartite graph containing at least one edge is 2. There is no clique of larger size in any bipartite graph. So even if you consider the complete bipartite graphs also, which is biclique, here also every clique is of size 2 only. So omega for any bipartite graph is 2. Now what about the independence number alpha? Now for any arbitrary bipartite graph, there is no formula to determine the independence number. But for complete bipartite graph Kmn, we can determine the independence number. What is it? We know complete bipartite graph has 2 partite sets. Each partite set is an independent set. So both the partite sets are independent sets. Now between these partite sets only one would be the maximum independent set, the one having the maximum cardinality. Now in a complete bipartite graph, for example, let's talk particularly about K32. So it is the graph containing 3 vertices in one partite set and 2 vertices in the other partite set. So it looks something like this, right? Now here the partite set capital U containing the vertices U, V, W is an independent set itself, and the other partite set containing X and Y is also an independent set. In any bipartite graph, the partite sets themselves create an independent set because they are mutually non-adjacent to each other. There is no edge between any 2 vertices of the same partite set. And in complete bipartite graph, what is the particular nature? It is like every edge that is possible having one endpoint in one partite set and the other in the other partite set is already drawn. So having an independent set like capital U, we cannot insert any more vertex in this set to extend this independent set. So this independent set is maximal. Similarly, the other independent set XY is also maximal because I cannot include any of the other vertices U, V, W in this set XY because X and Y both are adjacent to every vertex of the other partite set. So this is also a maximal independent set. Now of these, the maximum is U, V, W. So that will give me the independence number, which is 3 in this case. So alpha of K32 is 3. So basically by formula we can say Kmn has independence number is equal to maximum of the 2 integers m and n. Of these m and n, whichever is a larger value is the independence number of the complete bipartite graph, because both the partite sets are actually forming independent sets. Of these two, the one with the larger cardinality will give the independence number alpha. So these are basically those key points that we have just discussed about complete bipartite graphs. So now we have a practice problem session. So basically I will be posting a problem for you to practice, and I expect you to solve it and give me the answer to this problem in the comment section below. I will give you the solution to this problem in the very beginning of the next lecture. So let me discuss the problem for you and explain it to you. A complete bipartite graph Km12 has size 72. So basically you are given a complete bipartite graph Km12. So clearly the value of m is not provided to you. What you have been provided with is the size of this graph, that is it contains 72 edges, that is given to you. You have to find the value of m, and after that you have to determine the order of the graph. So you give me the value of m and you give me the order of this graph, that is how many vertices are there in this graph. Well, so that's all for today. I really hope that you are enjoying these learning sessions. So if you do have any queries or suggestions, please do write to us in the comment section below. I am going to meet you again in the next lecture. Till then, thanks for watching. Take care and bye-bye.